Welcome back to the next video, everybody. Today we're going to be examining the condition of modularity of an elliptic curve over the rationals more closely. Let's recall that we say an elliptic curve E over Q with a conductor N sub E is modular if there's a new form F in S2 gamma 0 with level conductor N sub E. So in other words, we're looking at a new form with trivial character here, such that the L function of F equals the L function of E. Although for these things to equal, you really only have to check that they equal each other. For example, at the prime indices at which E has good reduction. Okay, so we'll talk a little bit more about why that is later. But for now, here's the definition from last video. Okay, and these L functions were also defined last video. Okay, some needed terminology before we state the main theorem of the day. Let's denote by x sub 0 of n the modular curve associated to gamma sub 0 of n. That's the cuspidal compactification of a fundamental domain of gamma sub 0 of n. That might be a lot of jargon and nonsense to you. You should just think of the non-cuspidal points of this curve as corresponding to isomorphism classes of complex elliptic curves equipped with a cyclic subgroup of order n. And it turns out that this curve has a model over the rationals, even though it's initially defined as a complex curve. So that's discussed in chapter 3 of my notes. Those videos are already up on the channel. Okay. An abelian variety over a field K is a projective algebraic K variety with a group law defined by K regular functions. So it's a projective algebraic variety that's a group, basically. Okay. So for example, elliptic curves are one-dimensional abelian varieties. In fact, they are exactly the one-dimensional abelian varieties. So more on that later. An isogeny of abelian varieties, A1 and A2, is a surjective morphism from A1 to A2 that has finite kernel. And it turns out such a map must be a homomorphism of groups. Okay. If there's an isogeny from A1 to A2, then we'll just say A1 and A2 are isogynous. All right. So here's the big theorem of the day, the five-fold theorem, I call it. Let E over Q be an elliptic curve with conductor N. Then the following 5 conditions are equivalent. There are actually more than 5, but I picked the 5 that I think are the most enlightening and the most important. 1, E is modular. 2, there's a surjective Q morphism of Q curves from the modular curve x0 of N onto E. And N here is the minimal such integer satisfying this property. So N in this context is called the analytic conductor of E, and the conductor up here that we attach to E initially is usually called the algebraic conductor. And so what we're saying is the algebraic conductor matches the analytic conductor. Okay. 3, E is Q isogynous to the so-called abelian Q variety A sub F attached to F. So you can canonically attach an abelian variety to any new form. More on this later in chapter 3 of my notes, although again, those videos are already up. What's F? It's just some new form F in S2 gamma 0 of N with number field Q. Remember, the number field of a new form with trivial character is just the number field gotten by taking Q and adjoining all the Fourier coefficients of F to Q. And that turns out to be a finite extension of Q. So it's a number field. Okay, so 4 and 5 are big news. 4 says for some prime P, there's a new form F sub EP in S2 gamma 0 N of number field Q, such that the p-adic Galois representation attached to E is isomorphic to the p-adic Galois representation attached to F. Okay. And then it turns out, surprisingly, that you can replace the word sum here with each, and you get an equivalent condition. So for each prime P, there's a new form FEP in S2 gamma 0 N of number field Q, such that rho EP is isomorphic to rho F sub EP. Okay. So proof, where would you look if you wanted to see the proof of this? Diamond and Sherman, the book, is essentially all about how a bunch of different versions of modularity are all equivalent. That's what that book is basically about. It's preparing you to study for Fermat's theorem in some sense. There are many other conditions in that book that are shown to be equivalent as well. So I'd start there. There's also the Diamond-Darman-Taylor notes, page 47. There's also Diamond and Im's modular forms and modular curves, section 13. But then I also have a chapter coming up much, much later in my notes, chapter 19, that discusses the proof of this theorem as I've stated it in some detail. Okay. And then I'll just say, because it will use this, if an elliptic curve E over Q is modular with conductor N, you can of course conclude there's an isomorphism between the residual representations rho bar EP and rho bar F for some way to new form F in S2 gamma 0 N and for all primes P. Well, yeah. Okay. So next time we'll start looking at some of the more high-powered elliptic curve theory that's needed throughout the proof of this, because it's not that I'm interested in the proof of the five-fold theorem right now, but I am interested in a number of these results because they're deep results that are used at various points throughout the proof of Fermat's last theorem, and they're just important results about elliptic curves to know in general. So I think here's a good time to start mentioning them to you. So we'll do that beginning next video. So I'll see you all tomorrow. Thanks for watching.